everyone, my name is Ranjit Kaur, Assistant Professor, ABES Engineering College, Ghaziabad. Uh, Today's topic of discussion is expansion of functions of two variables. These are the outline of today's lecture, that is expansion of function of two variables, then statement of Taylor's and Maclaurin's theorem, then application to find the expansion of given function using these theorems. Here we are going to discuss why we need expansion of function of two variables. We need to expand a function so that it can easily be approximated at a point using its partial derivatives. It is used in error and approximation. It is also used to estimate a complex function and sometimes to approximate complex integrals. This is the statement of Taylor's theorem that let f of xy be a function of two independent variables x and y, and x plus h comma y plus k be a point in the neighborhood of xy for very small values of h and k. Then by Taylor series, function at neighborhood point can be expanded in positive powers of h and k using the partial derivatives as expressed in equation 1. There are some other forms of Taylor's theorem of two variables that to expand a function about a particular point x equal to a and y equal to b, then in the formula 1 we replace x by a and y by b and we get this formula number 2, that is another form of Taylor's theorem for point a comma b. This is another form of Taylor expansion to expand a function in powers of x minus a and y minus b. In this form, we replace h by x minus a and k by y minus b in equation 2. And we get this equation 3, that is function at xy is equal to function at particular point a comma b plus x minus a, function's partial derivative with respect to x at that particular point, plus y minus b, function's partial derivative with respect to y at that particular point ab, and so on. Then there is Maclaurin's theorem. Maclaurin's theorem is considered as a particular case of Taylor's theorem to expand a function about origin or point 0, 0. So we replace a by 0 and b by 0 in equation 3. That is, we get this formula function at xy is function at 0, 0 plus x times function's partial x at 0, 0 plus y times function partial y at 0, 0 plus 1 upon 2 factorial x square function double partial x with respect to 0, 0 2 times xy function's derivative of x with respect to y at 0, 0 plus y square function double derivative with respect to y at 0, 0 and again so on, and we turn as equation 4. Now we are going to discuss some examples on these forms. Here the statement is expand the function ex cos y in powers of x minus 1 and y minus pi by 4. The solution here, function is given, that is ex cos y, point A is 1, B is pi by 4. We are going to use formula 3, that is form 3. I am writing again, function at xy is function at 1 comma pi by 4 plus x minus 1 times function's partial derivative of x at 1 comma pi by 4 plus y minus pi by 4 function's derivative with respect to y at this particular point plus 1 upon 2 factorial x minus 1 whole square function double derivative with respect to x at 1 comma pi by 4 plus twice x minus 1 y minus pi by 4 functions partial xy at 1 comma pi by 4 plus y minus pi by 4 whole square function double derivative of with respect to y at 1 comma pi by 4 and so on. By default, we expand the function up to 2 degree terms. So here we are going to find all the derivatives which we need in this formula, that is function is ex cos y, function partial x f is ex cos y, functions partial y is minus of ex sin y, function double derivative of with respect to x is ex cos y, then function x with respect to y derivative is minus ex sin y, then function double derivative y at is minus of ex cos y. Now here we are going to evaluate this function at this particular point. Then function at 1 comma pi by 4 is e raised to power 1 cos pi by 4, that is e upon root 2. Function partial x at this particular point is again same e1 cos pi by 4, it is again e by root 2. Then function y derivative at 1 pi 4 is minus of e1 sine of pi by 4, which is minus e upon root 2. Then double derivative of x at 1 comma pi by 4 is same again, that is e by root 2. Functions mixed partial at 1 comma pi by 4 is minus e by root 2, and function double derivative with respect to y at this particular point is minus e by root 2. Now if this is the formula, now what we are going to do, we'll replace all these values in formula 1. So function, the left hand side becomes function, that is ex cos y is function's value at this point, and that is e by root 2. Here we will write e by root 2 plus x minus 1 partial x, that is again e by root 2 plus y minus pi by 4, then partial y is minus e upon root 2 plus 1 upon 2 factorial x minus 1 square e upon root 2 plus 2 times x minus 1 y minus pi by 4, it's minus e upon root 2 plus y minus pi by 4 square, and derivative is minus e upon root 2 plus so on. So finally we get ex cos y is equal to finally its value is e upon root 2 plus x minus 1 e upon root 2 minus y minus pi by 4 e upon root 2 plus 1 upon 2 factorial x minus 1 square e upon root 2 minus twice of x minus 1 y minus pi by 4 e upon root 2 minus y minus pi by 4 whole square e upon root 2 and so on. And this is the expansion of ex cos y about point 1 comma pi by 4. Now we are going to discuss one more numerical To expand this function f of xy, ey log 1 plus x in powers of x and y, or we may also say to expand this function about origin. So here function is ey log of 1 plus x. About origin means a is 0 and b is 0, and we are using Maclaurin's theorem, that is function at xy is function at 0 0 plus x times partial x at 0 0 plus y times partial y at 0 0 plus 1 upon 2 factorial x square times double partial x at 0 0 2 times xy partial xy at 0 0 plus y square function yy at 0 0 and so on. So here again, first we will find all the required derivatives which we want to replace in formula. Then this is the main function. Partial derivative with respect to x is ey upon 1 plus x, and by chain rule it is 0 plus 1. That is, it is the partial derivative with respect to x. Partial with respect to y is ey derivative is ey log of 1 plus x as it is. We may also write this answer like this for evaluating further derivatives. Now, per function's double derivative with respect to x is ey, derivative is minus 1, 1 plus x raised to power minus 2, or we may write e minus ey upon 1 plus x square. Then function x derivative with respect to y is, it is ey 1 plus x minus 1, or ey 1 plus x. Then function y derivative again with respect to y is ey log of 1 plus x. Now in parallel we will find all the derivatives at point 0 0. We will evaluate. Here, when we replace y by 0 and x by 0, we get e0 log of 1, that is log 1 is 0. Function partial x at 0 0 is e0 upon 1 plus 0, that is 1. Function y derivative at 0 0 is due to log, it is again 0. Function double derivative x with respect to 0 is minus 1 upon, so its value is minus 1 upon 1 square, that is minus 1. Function x is again e raised to power 0 upon 1, it is 1, and function double derivative with respect to y is 0 because of log. Hence, replacing all these values in above formula, we get ey log of 1 plus x is 0 plus x times 1 plus y times 0 plus 1 upon 2 factorial x square times minus 1 plus 2xy times 1 plus y square times 0. Or in compact form, we may again write it is x plus 1 upon 2 minus of x square plus 2xy plus so on up to, it is the expanded form of ey log 1 plus x about 0.00. And so this is the final answer. This is how we expand functions about origin. Thank you, everyone.